All right, for this quiz, we're looking at a calorimetry experiment where basically we take an iron bar, we get it really hot, we put it into a water bath, and we see what the change in temperature is. And with this, we want to determine what was the initial temperature of the iron bar ultimately, and this is going to break this into parts. So the first question that's asking, how will the energy change of the iron relate to the energy change of the water, is really getting at how we approach these from a big picture conceptual idea. Because that's the whole idea of calorimetry, is that because we know about certain properties of energy, we know that if something changes temperature, maybe we can detect how much energy something else may have lost. And so what I'm getting at here is really the key concept of this chapter and for this problem, and that is that energy is conserved. And how do we put that more strictly into math for this problem? Well, if energy is conserved and really the only energy movement we have in this problem is the heat into the water and out of the iron, we can say all of those added up together equals 0, right? We'll say Q water plus Q iron equals 0. And perhaps an easier way to think about this is that the energy into the water equals the energy out of the iron, and therefore one is equal to the other, making sure that we have this negative sign there to make sure that we show that it's out of one equals into the other. And this is literally the same thing as the conservation of energy, right? We just subtracted the iron from each side and we end up with this. So these are really the same equations, and when we're looking at this, this is conservation of energy, and it's really good to be able to specifically note it as such and to be familiar with both of these representations algebraically. The second thing we want to do is state the final temperature of both the water and the iron bar. And for this one, it may seem pretty straightforward, or maybe like there's more to it, but there's not really. I mean, it's just that heat transfer stops at thermal equilibrium, and therefore the final temperature for the water and the final temperature for the iron are both going to be 27.6 degrees Celsius, which is given in the problem. This is here just to emphasize that defining these variables strictly is really important, and that this thermal equilibrium that we reach is exactly the same for both of them and is going to be this 27.6. We'll use this value for both of these two substances moving forward. What is the amount of heat that flows into the water from the iron? And so as we look at this problem, we really don't have enough information to just detect how much heat flowed out of the iron directly. But what we do know is the initial temperature of the water. And therefore we actually have everything that we need to calculate the heat flow based on the specific heat capacity of water. And for that, we want to use the following equation, Q equals mc delta T. For here, I've put water in just to show that we're dealing with water. We know the amount of water that we're dealing with. We have the density and the volume of the water. We have the heat capacity, specific heat capacity of the water in the table below. And we know the final and initial temperature of the water. So let's lay out all of those things. The mass of the water is 500 grams. That's from 500 mils. Each mil is 1 gram. That's the density. So mass of water is given. Heat capacity of water is given, specific heat capacity. And the delta T is an increase of 7.6. We plug it in. And we are kind of stuck with only two significant figures here due to the temperature. And we therefore find that the Q water is 16,000 joules, or 16 kilojoules is what went into the water. Now, what about the iron bar before submersion? This could be just the only question that's asked in the problem. The rest of what we've done before has kind of led up to it, and this is kind of the heart of calorimetry, is that we can take an unknown heat generation process and figure out how much heat there is, and then figure out other things about that substance. So what is the temperature before submersion? That's what we're looking at here. And we want to tie together everything we've done, right? The Q water equals negative Q iron. And basically this tells us that the iron lost 16,000 joules because the water gained 16,000 joules. This is conservation of energy. From here, we do want to use Q equals mc delta T, but we don't actually have the change in temperature. However, because we have the heat, we can use that to calculate the change in temperature. And when you set this up, I really would just solve for change in temperature as a variable. I would not break that down into final minus initial. I think you'll find that it just really complicates the algebra, and we can just do a second calculation for the initial temperature after we solve for delta T. So plug everything in, leave delta T as a variable. We find out that the delta T is negative 710 degrees Celsius, which is to say that the iron bar lost 710 degrees Celsius. Delta T is T final minus T initial. This is always true whenever we have this capital delta, the triangle. It's always final minus initial. We plug this in, final minus initial is negative 710. We have the final temperature, we're looking for the initial temperature, and when we solve this, we find that it's 740 degrees Celsius. And so I think we want to assess this qualitatively at the end, right? We have an iron bar that's 1/10 the size of the water bath, and it makes the water bath rise only 7 degrees. So we have 100 times more temperature change for the iron than the water. Does that make sense? Well, actually, when we look at this, it does, because not only is there 10 times as much water, but there's also 10 times the heat capacity of water. As we see, the heat capacity of water is very high. It's about 4, whereas the heat capacity of iron is about 0.4, right? So it takes 10 times as much energy to bring water up 1 degree as iron. Therefore, if there's 10 times as much and it takes 10 times the energy to increase a single degree, it does make sense that the iron has had 100-fold more temperature change than the water.